Welcome to The Explainer. Today, we're diving into a single technology that could, seriously, tackle two of our planet's biggest headaches at the same time: how to get fresh water for everyone, and how to find enough lithium to power our clean energy future.
Think about this question for a second. It's a big one. We're surrounded by these massive oceans, right? But somehow, water scarcity is still a huge global problem. And at the exact same time, we are scrambling to build batteries for everything, which means lithium, and a lot of it. What if the answer to both problems is staring right back at us from the sea?
And this is why that question is so incredible. Our oceans hold over 60,000 times more lithium than all the land-based reserves we know of combined. The sheer potential locked away in seawater is just mind-boggling.
So that's what this explainer is all about. These two giant connected challenges. On one hand, you've got a basic human need, fresh water, and on the other, a major roadblock for the green transition. We're going to see how one really clever approach might just offer a single unified solution. Okay, so to get how we pull salt out of water, we first have to get how nature works. It all comes down to a process called osmosis. There's a really simple rule to remember here. Water follows the solute. Basically, water naturally wants to move from a less salty place to a more salty place to kind of even things out.
And this is the key. If we want to turn seawater into fresh water, we can't just go with the flow. We have to literally fight against that very powerful, very natural tendency of osmosis. And for a long time, this is how we've done it. It's called reverse osmosis, or RO, and it's basically a brute force attack. We use these incredibly powerful pumps, we're talking pressures 40 times higher than the air you're breathing, to literally squeeze pure water molecules through a superfine membrane, leaving all the salt ions behind. Now check out the energy cost on this chart. Modern RO plants are amazing feats of engineering, way more efficient than older methods. But even so, look at that bar on the far right. It still takes about 2 kilowatt-hours of electricity for every single cubic meter of fresh water. When you're talking about supplying a city, that energy bill gets absolutely enormous. And it's not just the energy bill. The leftover stuff, the brine, is now twice as salty as the ocean, and dumping that back can create real problems for marine life. Plus, before you even start, you have to clean all the gunk out of the seawater. The membranes are constantly getting clogged up. And then, after all that work, the water is too pure, so you have to add minerals back in so we can safely drink it. It's a messy, expensive process. So this brings us to a huge shift in thinking. What if, instead of fighting nature with all that pressure, we could just persuade the salt to leave? Not with a powerful shove, but with a gentle electrochemical nudge. This is the idea behind capacitive deionization, or CDI. It's so elegant. First, you apply a tiny bit of voltage to these special porous electrodes. That creates a weak electric field that just coaxes the salt ions, the positives and the negatives, right out of the water, where they stick to the electrodes. Then you just turn off the voltage, and the ions release into a separate, concentrated stream. What's left behind? Fresh water. It's that simple. Charge, capture, release. And listen, this isn't some sci-fi concept that just popped up. As you can see from this timeline, the basic idea has been around since the 1960s. But it's the recent breakthroughs in materials and designs, like membrane CDI, that are making this technology a serious contender right now. And the advantages? They line up perfectly against all the problems with reverse osmosis. We're talking low energy input, not high pressure. We're talking mild operating conditions, no intense heat. The whole setup is simpler, and maybe most importantly, the environmental impact is way lower. It just elegantly sidesteps all the major drawbacks. All right, let's switch gears back to that second challenge, lithium. Take a look at this. In just about a decade, global demand for lithium has nearly quadrupled. That's the mountain we have to climb for the clean energy transition, and it's putting a massive strain on our current mining operations. So here's the next puzzle, right? Seawater isn't just sodium and water. It's a complex chemical soup with all sorts of ions floating around: magnesium, calcium, potassium.
An electrochemical system is great at grabbing ions, but how do you get it to be picky? How do you tell it to only grab the valuable lithium?
And this is where the real magic happens. Scientists are creating these amazing ion selective membranes. Think of them like an atomic scale bouncer at a club. For example, a material called ziphate has these tiny, tiny channels. To get through, an ion has to shed all the water molecules clinging to it. Well, it turns out a dehydrated lithium ion is super small, so it can zip right through. But the bigger ions, like sodium, they can't fit. They're blocked. It's a sieve at the atomic level.
And this is the part that changes everything. That concentrated stream of ions, the stuff that was a toxic waste product in the old RO system, is now a valuable resource. We're not just solving a disposal problem, we're creating a new supply chain. This is what a true circular economy looks like.
Let's just put it all side by side. It couldn't be clearer. Traditional RO, high pressure, high energy. The electrochemical method, low voltage, low energy. RO is like a sledgehammer. It takes out all the salts. This new approach can be like a scalpel, targeting just the ions you want. And the bottom line, RO leaves you with polluting brine. The electrochemical method leaves you with a stream of valuable resources. It's a completely different philosophy.
Now, of course, this isn't running the world just yet. There's still critical work to be done. Researchers need to move this out of the lab and into the real world. That means testing it on actual, messy seawater, not just clean lab solutions. It means making these amazing membranes durable and cheap to produce. And it means scaling everything up from tabletop experiments to pilot plants that prove this can work on a massive scale.
But the vision here is just so powerful. It asks us to completely rethink the ocean, not as something to be conquered, but as a sustainable, dual-purpose resource that can simultaneously solve our water crisis and fuel our technological future.
Answering that question is what cutting-edge science is all about. If you're as fascinated by these kinds of transformational technologies as we are, then make sure you subscribe to E3 Nexus Lab for more explainers like this one. Thanks for joining us.